Welcome to Ready to Derive. In this video, we will be looking at three inverse trig functions and their derivatives. The first one is inverse sine x, aka arcsinx, which I want you to read as the angle whose sine is x. We will be deriving the derivative of inverse sine x, and then I will be giving you the formulas for inverse cosine and inverse tan. We won't treat the reciprocal trig functions in this video because we have plenty of practice to go with here. So without further ado, let's get started. So let's take a walk down memory lane and do a brief precalculus review of inverse trig functions. So why do we even need inverse trig functions? And that's to solve equations of the form sine of x equals 0.5, for example. So we know that if, say, we wanted to solve the equation as a comparison x squared equals 10, we know that we would have to use the inverse function. The inverse of squaring is square rooting, and we would type that into our calculator and get the answer that way. So the inverse of sine is nothing else but inverse of sine. So if sine x equals 0.5, then x by definition is the inverse sine of 0.5. So now if I plug this into a calculator, I'm going to be in degree mode. That gives us an angle of 30 degrees. And we probably should have seen that coming, that we know that an angle in the first quadrant, angle of 30 degrees, has a sine of a half. Now, what the calculator can't give us is the fact that there is another angle whose sine is a half. That's in the second quadrant. So it would have the same reference angle of 30, which would put that at 150 degrees. Notice that the inverse trig function, or any inverse function, can only generate one answer. And you really have to think about the other possible solutions. So let's try and do the thinking ahead of time now. So look, if we know that the sine of x is now negative 0.5, this is what we would type into our calculator. But before we do, let's try and predict what the angles would be. So sine is negative in quadrants 3 and 4, and therefore if we take that reference angle of 30 and put it into these two quadrants where sine is negative, we would get an angle that this would work. This is 180 plus 30, that would be 210, and this would be 360 minus 30, so that would be 330. So I don't know, let's predict what it will give us when we put that in the calculator. I'm thinking 330 because that's kind of closest to the positive x-axis. But look what happens. If we type that in to our graphing calculator, it actually, instead of reading that as 330, it reads that angle as negative 30 degrees. So it reads this angle as it rotates 30 degrees in that direction. So we really have to pay attention to what inverse sine is going to deliver and in what quadrant it's going to put that angle. And that's what we'll take a closer look at in the next slide. So to understand at least the range of inverse sine x, let's go back to the basics. Let's go back to a graph of y equals sine x. And if we recall that to create the inverse relation, you would just reflect the graph over the line y equals x, and that would cause the inverse to snake up the y-axis like that. That's a mirror image over the line y equals x. Well, we can see that the inverse graph, inverse sine, is not a function right now. It fails the vertical line test, and that's because sine itself fails the horizontal line test. So we need sine to be 1 to 1, and if you recall from precalculus, we achieve that by restricting the domain of sine x from negative pi over 2 to pi over 2. And in so doing, so we restrict that domain from negative pi over 2 to pi over 2. And in so doing, the range is we still cover negative 1 to 1, every value. But by restricting it that way, we create, so if we now reflect that over the line y equals x, and we create that inverse sine function, which is indeed a function. It passes the vertical line test. And from that, we can see that because it's the inverse function, the domain and range flip. So the domain of inverse sine is negative 1 to 1, and the range, and this is the most important part, is to understand that inverse sine will only ever deliver you an angle between -90 and 90, which would explain what we discovered in the previous slide about the inverse sine of -0.5. So now we actually get to the fun part, which is to use calculus to derive the derivative of inverse sine x, because that's how we roll on Ready to Derive. So let's begin by defining y to equal the inverse sine of x. Now, it follows that, and we saw this before, but if this is true, then it must also be true that sine y equals x. And if you're having sort of trouble reasoning through that, you can think of just taking the sine of both sides, if that helps. And the sine of the inverse sine, because they're inverse functions, they'll undo each other. And now we're going to do some implicit differentiation. So let's use implicit differentiation, and we would get the derivative of sine is cosine of y, but we mustn't forget, since y is itself dependent on x, we would, by the chain rule, have to be multiplying by dy by dx on the left-hand side, and the derivative of the right-hand side would be 1. Okay, so now let's isolate dy by dx, since that's what we're interested in, and we get 1 over cosine y. The thing is, if this is a function, then we really want the derivative formula in terms of x. So we're going to do a neat little trick here using some right triangle trig. And let's go back to the basics. So we know we defined y in such a way that this would be true. Sine y equals x. You can think of that as x over 1. And then you can think, well, sine is technically the ratio of the opposite to the hypotenuse. So let me put that information into this diagram. So let's call that angle y. The side opposite that angle should be x, and the hypotenuse should be 1. And we are interested in finding an expression for cosine of y. Well, cosine of y would equal the adjacent over the hypotenuse, but we don't know the adjacent. So let's call that a, but we could find it out in terms of x if we just use the Pythagorean theorem. So we would get a squared plus x squared equals 1 squared. And if we isolate a squared, 1 minus x squared, and then take the square root, and it would be the positive square root because we're talking about length here. And we get that a is rad 1 minus x squared. So that's the adjacent, 1 minus x squared, and the hypotenuse is 1, which allows us to come over here, and in place of cosine y, we would just replace that with what it is in terms of x. And that gives us a formula for the derivative of the inverse sine of x. It's 1 over the square root of 1 minus x squared. So in the interest of time, I'm just going to summarize, going to give you the derivative formulas for inverse cosine and inverse tan. If you'd like to prove it, you can prove those results. You can do so following sort of the same steps as we did for inverse sine. But here we go. The derivative of inverse cosine is very similar to inverse sine, but it's just the opposite. It's just -1 over the square root of 1 minus x squared. And the derivative of inverse tan is kind of a nice one, actually. It's just 1 over 1 plus x squared. And the domain for inverse cosine naturally is the same as for inverse sine, but this is slightly different. Again, you'd have to go back to precalculus to sort of understand why it is this case, but the range of inverse cosine is 0 to pi, so it delivers you angles only in the first and second quadrant, whereas inverse sine gives you angles in the fourth and first quadrant. And by the way, inverse tan is similar to inverse sine because sine and tan are both odd functions. So let me put this here first. The domain of inverse tan is all real numbers, but the range is very similar to that of inverse sine, except of course we can't get angles pi over 2 and negative pi over 2 out because we know that the tan of pi over 2, negative pi over 2 is undefined. So, and as a quick review, let's just sort of pop these out just to see the pattern. So the inverse sine of a half we know is 30 degrees. We'll work in radians now. It's pi over 6. And we know that if it was a negative input, we would have to put it into the fourth quadrant as a negative angle. So if the inverse cosine of 0.5, again, in quadrant 1, if the input of these inverse trig functions is positive, we know we're going to be in quadrant 1. So that's pi over 3. This is a little tricky. Think about that for a moment. It's got to give you an angle between 0 and pi. So this is going to be in the second quadrant. So it's going to be 2 pi over 3. And now inverse tan. The angle whose tan is 1 is pi over 4. And the angle whose tan is negative 1, well, that goes into the fourth quadrant as a negative angle. So like inverse sine, it's going to deliver a negative angle, negative pi over 4. So it might be a good slide to pause on and just make sure you take down these comprehensive notes. So for our first practice problem, we're going to find the derivatives of the following composite functions. And for that purpose, if we realize why is this a composition of functions, it's because we have an inner function here. Let's call that u. So we have to, if I told you x was a value, you'd have to multiply 4 by it and then subtract it from 1. So that's kind of the inner function, and arcsine is the outer function. And I'm going to bring up this variation on the definition of the derivative that's reminding us to take the derivative of the inside function. So let's just apply this. So if we want to find dy by dx, then the derivative of our arcsine is 1 over the square root of 1 minus the input squared. And that input is u, which is 1 minus 4x. But we mustn't forget to multiply by the derivative of the inside function, which would be negative 4. So we can tidy that up, but we're not going to simplify this anymore, even though you probably could FOIL out that squared parentheses and simplify it somewhat. And now for the other one. Okay, same idea, but now we're dealing with the derivative of inverse cosine, and that's the outside function. So using correct notation, I'm going to say that's f prime theta. We're taking the derivative with respect to the variable theta. Once again, the derivative of arc cosine, let me set this up. It's 1 minus, what we mustn't forget to put in there is the value of u. What is u? That's the inside function is u. So in there we put e to the theta squared, and then we multiply by the derivative of e to the theta squared, which is a chain rule in itself. So it's the derivative of e to any function is e to that function times the derivative of the inner function, theta squared, which is 2 theta. So then we get, if we just tidy it up a bit, we get this on the numerator. And on the denominator, we could remove that parentheses by noticing that will be e to the 2 theta squared. Not e to the theta to the 4th, because we are just multiplying the exponents theta squared and 2. So now we'll find the derivative of this function, and then we will practice simplifying after the fact. So again, the inside function, the inner function is 3 over x. We'll call that u. And I'm doing this a little bit to the side here so we don't make any mistakes in finding du by dx. So 3 over x is really 3x to the minus 1, which means du by dx by the power rule will be negative 3x to the minus 2, or negative 3 over x squared. And now let's bring up the formula. So for the derivative of arctan is 1 over 1 plus the input squared. And again, to keep the chain rule in mind, we're going to multiply that by du by dx. So that means that f prime x is the derivative of arctan, the outer function, is 1 plus the input squared. And that input, that inner function, is 3 over x. And then du by dx, we just determined, is negative 3 over x squared. So let's tidy this up a little bit. We have negative 3. In here, we could sort of expand 3 over x squared. That will be 9 over x squared. And then we have an x squared. This x squared here just sort of hanging around outside. So why not distribute that in to the parentheses, and we get negative 3 over x squared plus 9. And that is our final simplified answer. So for the last practice problem, we're going to find the equation of the tangent line to this inverse cosine curve. So let's first of all call up the equation of a tangent line and realize that in this case a is negative 1. So we really want to find f of negative 1. That will give us the y-coordinate that corresponds to x equals negative 1, and then also the slope of the curve at negative 1. And x minus negative 1 becomes x plus 1. So let's move over here. Let's start by finding f of negative 1. So we just plug negative 1 in place of x, so we get inverse cosine of negative half, 3 times that quantity. And we know from before that inverse cosine delivers angles in the quadrants 1 or 2, and because the input is negative half, it must go into quadrant 2. The reference angle is pi over 3, so in quadrant 2 this would look like 2 pi over 3. Notice the 3's cancel and we have 2 pi. So we already have that part. Now we have y minus 2 pi equals, we have x plus 1 here, and we just need to find the slope. So let's take the derivative of the function first. That 3 is just a coefficient, so that can kind of just tag along. So we're going to get the derivative, of course, it will be negative 3 over the square root of 1 minus the input squared. And then we have to multiply by the derivative of the inside function. And x over 2 is really just the same as a half x. So the derivative of a half x is just 1/2. And if we tidy this up a little, we get negative 3 over 2. We'll keep that in the denominator there. 1 minus x over 2 squared. We don't have to simplify too much because we are just plugging in. We are trying to find the slope f prime at negative 1. So we will plug in and we'll get 1 minus, and in here we'd get negative 1/2 squared. And that becomes negative 3 over 2. Now, half squared is a quarter, and 1 minus quarter is 3/4. So I'm just going to simplify what's there under the radical and tidy up a little more. Square root of 3/4 is really just the square root of 3 over the square root of 4, which is 2. So these cancel. And now I could work with the slope in that form. We could also rationalize the denominator, and we would get 3, rad 3 on the numerator over 3. Those cancel. All that work to, don't forget the negative, so all that work to get that the answer for the slope is negative rad 3. So this is the equation of the tangent line, and what I did is I tested it in Desmos. So there's the function f of x, the inverse cosine function, and then what I did is graph that tangent line, and it went perfectly through the point -1, 2 pi. And that brings us to the end of this lesson. I hope you found it helpful, and if you did, please do click like and/or subscribe to my YouTube channel, Ready to Derive. Thank you.